Swayam Prabha. Digital India. Educated India.
Effluent testing, lecture number 7. In the past we have seen that textile effluents have different loads and some regulatory norms have been set up, and unless and until we do the testing of effluent, we will not know what is the load of organic matters, what is the COD, what is the BOD, what is the TSS, etc. Hence, I thought of dedicating one full chapter or lecture for effluent testing. How is it done? What are the parameters that should be kept in mind while understanding the textile effluents composition and its level permissible by the regulatory bodies. Parameters for pollutants. Parameters for pollutants, testing of pollution parameters, regulations in developed countries and eco-friendly processes. These are some of the topics that we will cover in this lecture. Effluent testing. Textile effluent constitute the largest proportion of the total industrial effluent, and this we have seen in the past that in the last few lectures I have been telling that the most polluting industry is the textile industry. Effluent testing is thus imperative to protect the environment from adverse effect of the effluents. The samples have to be analyzed for different metals, biological oxygen demand, that is BOD, suspended solid, that is SS, fats and oils and grease, which is abbreviated as FOG, nitrogen, phosphorus and several total toxic organics, which is TTOs. The effluent testing refers to the process of analyzing the wastewater or discharge from the industrial, commercial, municipal sources to determine its chemical, physical and biological characteristics. This testing is essential to ensure compliance with the environmental regulation, assess potential impact on ecosystem and public health, and monitor the effectiveness of treatment processes. So, unless and until we do a testing of influent and effluent and their characteristic of COD, BOD, TSS and other parameters like nitrogen, phosphorus and total toxic organics, total organic pollutants, we will not be able to know whether the technologies that we adapted for purification or remediation of textile effluents are working or not efficiently. Key aspects of effluent testing. Regulatory compliance. Effluent testing is often required by regulatory bodies to ensure that discharge wastewater meets specific standards and does not harm the environment or human being. So, that is one of the primary concern when we talk about the textile effluent and its testing. Pollutant monitoring. Effluent testing involves the analysis of various pollutants such as heavy metals, organic compounds, nutrients, nitrogen, phosphorus, pathogens and pH levels. These pollutants can have detrimental effect on aquatic life, soil quality and overall ecosystem's health. So, pollutant monitoring unless we know how much is the level, how do we plan a strategy for effluent treatment? So, it is effluent testing is very crucial, not only for regulatory and compliance purposes, but also to know what are the levels of pollutants. Sample methods. Effluent sampling must be conducted using proper techniques to obtain representative samples. Samples are typically collected at predetermined intervals and locations within the wastewater treatment or discharge system. So, it should be, even the sampling has to be done very systematically. It is not that one can do any random sampling, keep it for days and then analyze. The sample will get further deteriorated and we will get different results than what exactly existed in the effluent at that time. Key aspects of effluent testing: analytical techniques. Various analytical techniques are employed to measure the concentration of different pollutants in effluent samples. These techniques may include spectroscopy, chromatography, titration and microbiological assays. So, different types of analysis need to be done in order to do the effluent testing. Quality assurance and quality control measures are crucial to ensure the accuracy and reliability of effluent test results. This includes calibration of instruments and adherence to standardized protocol and participation in proficiency testing programs, because it is very important whether my test method is correct or not and whether it has a repeatability or not, because just by doing test one time does not ensure that it is the correct result. Data interpretation: once the effluent testing is completed, the data obtained are interpreted to assess compliance with regulatory requirements and to identify any trends or abnormalities that may require corrective action. Treatment optimization: effluent testing can be used to evaluate the effectiveness of wastewater treatment processes and identify opportunities for optimization or improvement. So, unless and until we are testing the effluent and monitoring it, we will not know whether our remediation strategy is working properly, whether there is any abnormality or whether there is everything is happening in the correct manner. So, testing is required at every stage and all the parameters need to be repeatedly tested to monitor whether they are continuously reducing or not. That would emphasize whether the process of remediation is the correct method or not. Treatment optimization: effluent treatment and effluent testing go hand in hand. Effluent testing can also be used to evaluate the effectiveness of the wastewater treatment processes and identify opportunities for optimization or improvement. Effluent testing plays a vital role in protecting the environment and public health by ensuring that wastewater discharges are properly managed and do not pose risk to ecosystems or human populations. Physical parameters that need to be tested. Effluent testing involves the analysis of various parameters and pollutants to assess the quality of wastewater discharge. Here are some common parameters and pollutants that are typically tested. By physical parameters, which means that temperature, pH, turbidity, these are all under the category of physical parameters. Temperature. The temperature of the effluent can affect the solubility of various pollutants and influence biological processes. Hence, that needs to be corrected very effectively. pH. pH levels indicate the acidity or alkalinity of the effluent, which can impact aquatic ecosystems and the efficiency of treatment processes, because too high a pH or too low a pH, which could be high pH means alkaline, severely alkaline, and low pH means severely acidic, can affect the aquatic ecosystem. Turbidity. Turbidity measures the cloudiness of the water caused by the suspended particles, which can affect light penetration and aquatic habitat quality. So, I had mentioned earlier in one of the previous lectures that turbidity is equally notorious, because all these suspended particles do not let sunlight penetrate into the water bodies, and all the aquatic plants which are dependent on their photosynthesis on the sunlight do not get sufficient sunlight. As a result, they die out, and therefore, this turbidity can be quite notorious. Then comes the analysis of chemical parameters that needs to be tested. Among the chemical parameters, nutrients, this includes nitrogen in the form of ammonia, nitrate or nitrite, and phosphorus, which can contribute to eutrophication and algal blooms in receiving waters. So, they need to be tested. Heavy metals, metals such as lead, mercury, cadmium, chromium and arsenic can be toxic to aquatic life and bioaccumulate in the food chain. So, analysis of these heavy metals and their presence in the textile effluent is very, very important. Remember that I had told in one of the previous lectures that these heavy metals can be endocrine disruptor, they can be skin irritant, and they can even have an adverse effect in our gut metabolism. Organic compounds, organic pollutants such as polycyclic aromatic hydrocarbons, that is PAH, volatile organic compounds, that is VOC, pesticides and industrial chemicals can be harmful to aquatic ecosystem and human health. So, they need to be analyzed. Chlorine. Chlorine and its derivatives are often used in disinfection processes, but can be toxic to aquatic organisms if present in high concentration. And if you may recall, we had studied the chlorine dioxide oxidation method. There also we studied that this chlorine dioxide can be toxic to aquatic organisms if it is present in high quantities. So, all these need to be tested properly, so that they are not any longer harmful to the aquatic ecosystem or to human health. Then biological parameters also need to be tested. Biochemical oxygen demand, which is BOD. BOD measures the amount of oxygen consumed by microorganism while decomposing organic matter in the water. High BOD levels indicate the presence of organic pollutants and can deplete dissolved oxygen levels, harming aquatic life. Oxygen demand, chemical oxygen demand, that is COD, measures the amount of oxygen required to oxidize organic and inorganic compounds in the water. It provides a broader assessment of organic pollution than BOD. Pathogens. Effluent may contain various pathogens such as bacteria, virus and protozoa, which can pose risk to public health if discharged into receiving waters or used in irrigation. So, even the biological parameters are of prime importance and their assessment is very important, their analysis is very important in order to know the levels. How is the effluent testing being done? Now, that is the question, because now we know it is important to test, but how do we go about doing this test? What are the norms of testing? Effluent testing typically involves the analysis of these parameters and pollutants using various laboratory techniques including spectrophotometry, chromatography, titration and microbiological assays. So, these are 4 different categories of analysis system. Regulatory agencies establish permissible limits for these parameters and pollutants to protect environment and human health, and effluent testing helps ensure compliance with these standards. So, regulatory bodies have made these testing limits. There are limits for this, should be the COD value of a textile effluent that is leaving the factory, or the textile effluent which is being run into the nearby river. Similarly, this is the BOD permissible limit, this is the TSS permissible limit. So, limits have been set. Beyond that, the textile effluent would still need to be remediated before it can be run out for discharge, for the final discharge. So, that is something that needs to be kept in mind. Now, when we look at this chart, we see that pollutants found in textile effluent and their typical quantities. So, average BOD should not, it is normally 264 milligram per liter, average suspended solid should be 36, fat, oil and grease FOG should be 15 milligram per liter, ammonia nitrogen should be 0.31, total Geldar nitrogen should be 20.68 or 21, total phosphorus should be 0.53, mercury cannot exceed more than 0.0002, that is ppb level, cadmium should not be present at all, copper, chromium, you see they are all in parts per million level. And if we go on to see that total metal content should not exceed more than 0.37 milligram per liter, including all these iron, nickel, lead, zinc, silver, arsenic, selenium, molybdenum. So, looking at this, one has to now strategize the testing, and parameters and pollutants need to be kind of taken very seriously. Biological oxygen demand is the rate at which the microorganism use the oxygen in water while stabilizing decomposable organic matter under aerobic conditions. It is used as a measure of the organic strength of waste in water and the environmental impact of chemical pollution. When organic matter, that is the pollutants in wastewater, is plentiful, microorganisms may grow so rapidly that they may deplete the dissolved oxygen or to the extent that levels can be harmfully low for fish and aquatic life. So, that is the major concern, that BOD should not rise so much that the aquatic life cannot get oxygen, because all the dissolved oxygen will be consumed by the microorganism for assimilation or degradation of these organic pollutants, and it will not be available for the fishes or the other aquatic animals and plants. Generally, municipal wastewater treatment are capable of reducing or removing moderate to high levels of BOD, but in some cases pre-treatment is necessary. BOD to a certain extent can be beneficial in a septic system. BOD varies widely from industry to industry. Metal finishing wastewater has BOD less than 200 milligram per liter, whereas food processing in the tens of thousands and wool production contributing to 400. Municipal waste itself has a BOD of 120 milligram per liter. So, it varies. Suspended solids SS and fat, oils and grease, that is FOG. These pollutants are generally oxygen consuming waste in water's body. Acceptable limits are 168 milligram per liter for suspended solids and 250 grams for FOG. Nitrogen, ammonia, ammoniacal nitrogen and phosphorus. Phosphorus and nitrogen are nutrients that promote the growth of algae and larger vegetation. Too much algae and vegetation can become an interference, and as the algae breaks down, dissolved oxygen is consumed. Several years ago, phosphates were considered a serious problem for water bodies, and this led to regional ban on phosphate containing detergents, which was significant source of such pollution. Depending on the receiving stream, the phosphorus and nitrogen can be wanted addition or unwanted pollutant. So, ammoniacal nitrogen is a toxic chemical and can be harmful to fish. It also could cause oxygen depletion and is difficult to treat biologically. All three of these pollutants from textile wastewater point of view are very important. So, we cannot ignore nitrogen or ammoniacal nitrogen or phosphorus, because all of them put together have an adverse effect or have an adverse load on the textile effluent. Metal and fatty acids in wastewater. Metals in wastewater, we have seen, if not removed prior to entering the municipal treatment system, are either transferred to the sludge and accumulate or pass through the treatment system as effluent. These metals can be toxic to aquatic life, especially if they are bioaccumulative, and if metal concentrations are too high in the sludge could be considered as hazardous waste. So, metals have to be analyzed, and we saw a list of metals, and we also saw that total metal content cannot exceed more than 0.37 milligram per liter in any wastewater that is permissible to be let out. Metals are tested by atomic absorption spectrometer, that is AAS, or inductively coupled plasma spectrometer. Total toxic organics, total organic, semi-volatile organic, pesticides are listed as water pollutants by Pollution Control Board and are tested very carefully by either chromatography or by chromatography and mass spectrometry, that is GC or GCMS. Fatty acids like dodecanoic acid, hexadecanoic acid, octadecanoic acid, more commonly known by their name as lauric acid, palmitic acid and stearic acid respectively, are detected in the 1 to 4 parts per million range in most textile effluents. Water quality data of these acids are as follow. Lauric acid, which is dodecanoic acid, is used for alkyd resin, cosmetics, insecticides, food additives, wetting agents, soaps and detergent. In testing, it had no effect on rats fed a diet of 35% of lauric acid for 2 years. So, they are not as bad as heavy metals or other organic pollutants, but they are bad and they need to be removed. Palmitic acid is found in sewage effluent at 0.1 milligram to 11 milligram per liter and is considered a lethal dose for goldfish. So, one is not so harmful, but the other one is extremely harmful. Other chemicals like 2-butoxyethoxyethane, ethanol, this is known as diethylene glycol monobutyl ether or Dow-1-enol DB and is common industrial solvent as cleaner, detergent and soap. It is the glycol ether family, which is the Clean Air Act hazardous air pollutant, and a SARA 313 form R reportable class of chemicals. So, it is equally toxic. Phthalates, the phthalates in the wastewater stream are mainly due to the detergent and or sizing used at the textile plant. The prominent phthalates in textile effluent are diphenyl phthalate and di-N-butyl phthalate. Then comes the category of trichloroethylene. Trichloroethylene is used as a solvent for degreasing cotton, wool, etc. Solvents for dyeing trichloroethylene would be a concern for discharge to the septic system. The US Environmental Protection Agency, that is USEPA, drinking water standard is trichloroethylene up to 5 ppb parts per billion. Since trichloroethylene is very mobile in groundwater, there is a possibility of groundwater contamination and thereby contamination of nearby drinking water wells. So, it is quite toxic. So, testing of pollutant and pollution parameters, first comes the color and physical appearance. Color and physical appearance. Dye house base are the most important effluent as they are intensely colored and impart turbidity. Observation of the color is the primary test to determine the line of treatment. So, first when the effluent comes to the laboratory, its color and turbidity are assessed. Then comes the odor. Some of the effluent possess toxic substances which give offensive odor. This type of effluent needs special treatment. Temperature. Temperature measurement is a necessary and is done at the time of sampling itself, because if you recall, in one of the lectures I had told that sometimes the effluent coming out of the machine can have as high a temperature as 90 degrees. So, and the permissible limit is only 42 degrees. So, it has to be measured at the time of collection of the sample. pH value. pH of the wastewater indicates the acidic or alkaline nature of the effluent. It helps in two ways. It is useful to determine the type of treatment to be applied to the effluent, and it also helps in determining the efficiency of the applied treatment method. Then comes the testing of total suspended solid, TSS. The undissolved matter present in the effluent is referred as suspended solid. Determination of the suspended solids help in estimating the pollution potential of the effluent. It also helps in determining the load on secondary biological treatments after the removal of settleable solids in primary settling tanks. So, this is also important because all the suspended solids are the ones which create the turbidity, and if it is very turbid solution, then we know that the sunlight cannot penetrate through that. So, the aquatic life gets disrupted. Total dissolved solids. The determination of dissolved solids help in estimation of the dissolved minerals present in the effluent. Biological oxygen demand BOD. The measurement of dissolved oxygen indicates the purity of water or the effluent and is important for maintaining aerobic conditions in the water. It is the test of reflection of the pollution strength of the effluent and the rate at which the biochemical oxidation would take place. So, it is an indicative of how much oxygen still persists in the dissolved oxygen still persists in the effluent. Chemical oxygen demand. This test determines the pollution strength of the textile effluent by measuring the oxygen requirement of organic and inorganic matter in the effluent. Regulations that are developed in developed countries, because it was felt that there is a need for having clean water and we cannot keep on polluting all our water bodies. Currently, the Federation Clean Water Act CWA in United States have set up the basic requirements for regulating toxic substances that can be discharged to water supplying systems. Even EPA recommended an integrated approach for controlling toxic pollutants that uses whole effluent toxicity testing to complement the chemical specific analysis as means to protect both aquatic life and human health. The whole effluent tests. Aquatic organisms are exposed to various dilutions of effluent for a specific time period in order to predict at what level the effluent may cause harm to the others. Another approach developed is to have structural and functional indices that can be used to evaluate the effect of chemicals on communities maintaining under controlled laboratory conditions. So, there are ways that these federation and the EPA Environmental Protection Agency have found that these need to have regulatory system in place, so that people know that this is permissible and this is not permissible. So, the first one, that is the WET, deals with the chemical already in the environment, while the other is developing ecosystem levels indices used to evaluate chemicals before they reach the environment. Addressing water toxicity creates an even greater cost for the textile mill in terms of production inefficiency and increased production costs by using dyes and chemicals to comply with water quality regulation. So, now the rules have become very stringent. If they are using any kind of dyes and pigments and other organic auxiliaries in their processes, the manufacturers are made responsible to see that these are mitigated properly. For this purpose, the mill must conduct a toxicity identification evaluation to determine the specific agents causing the toxicity and must either replace or reduce their use. So, such stringent rules have been laid down because it has been felt that now is the time that one has to take an action before it gets too late. Effluent testing regulations in developing countries can vary widely depending on the country's specific environmental challenges, industrial activities and level of economic development. However, several common themes and approaches can be observed. Basic regulatory framework. Many developing countries have established basic regulatory framework to control pollution and protect water resources. These frameworks may include law, regulation and standards that govern wastewater discharge, effluent quality and environmental protection. Water quality standards. governments in developing countries often set water quality standards that specify permissible limit for various parameters and pollutant in effluent discharge. These standards are typically based on scientific assessment of potential environment and human health impacts. Now, textile effluent testing parameters. We have already seen that these parameters have been identified and there are defined methods of testing. Effluent testing in textile processing involves analyzing the wastewater discharged from the textile manufacturing facilities to assess its quality and compliance with environmental regulation. So, that is the main function. Textile effluent can contain various pollutants including dyes, heavy metals, organic compounds and suspended solids, which can pose risk to aquatic ecosystems and human health if not properly managed. Here is an overview of the parameters typically tested in the textile effluent testing. And we learned a while ago that color is one of the most apparent problems that we see. Textile dyes can impart vibrant colors to fabric, but can also result in highly colored wastewater. Effluent color is often measured spectrophotometrically and is an important parameter to monitor, as it can indicate the presence of dyes and other pollutants. Chemical oxygen demand COD. Repeatedly I am telling that these are the main culprits of textile effluent. COD is a measure of the amount of oxygen required to chemically oxidize organic compounds in the effluent. High COD levels indicate the presence of organic pollutants such as residual dyes, sizing agents and other processing chemicals. Biochemical oxygen demand BOD. BOD measures the amount of oxygen consumed by microorganisms during the biological degradation of organic matter in the effluent. Elevated BOD levels can indicate the presence of biodegradable organic pollutants, which means that which can deplete dissolved oxygen levels in receiving water bodies and harm the aquatic life. So, time and again I am telling the significance of testing color, COD and BOD as well as TSS. pH levels influence the solubility and chemical properties of pollutants in the effluent. Textile processes may involve the use of acidic or alkaline chemicals for dyeing and finishing, leading to fluctuations in effluent pH levels that can impact the aquatic ecosystem. Total suspended solids. TSS refers to the concentration of solid particles suspended in the effluent. These particles can include sediments, fibers and other insoluble materials discharged during the textile processing. Heavy metals. Textile effluent may contain heavy metals such as chromium, lead, cadmium and copper, which can be toxic to aquatic organisms and persist in the environment. The major problem is not only the toxicity, it is the persistent nature of these heavy metals that causes bigger problem. So, the effluent testing typically includes analysis of heavy metal concentration to ensure compliance with regulatory limits. Dye concentrations. Effluent testing may involve measuring the concentration of specific dyes used in textile processing. Some dyes are known to be persistent, bioaccumulative and toxic, posing risk to the environment and human health. So, pH and total suspended solids we have just seen. Surfactant and chemical additives. The textile processing often involves the use of surfactants and detergents and other chemical additives. Effluent testing may include analysis for these compounds to assess their environmental impact and ensure compliance with regulatory limits. Effluent testing in textile processing is essential for identifying potential environmental risk, ensuring compliance with regulatory requirement and implementing pollution prevention measures. By monitoring effluent quality and implementing appropriate treatment technologies, textile manufacturers can minimize their environmental footprint and promote sustainable practices in the industry. So, textile effluent testing, why is it important? What is the significance? First, of course, we know that we should know the level of pollution that it can create. Then the remediation plan can be strategized according to the level of the load, and this becomes the major responsibility of textile manufacturers to take care of this in order to have low environmental footprint and promote sustainable practices. Regulations in developed countries. Permitting and compliance. Regulatory agencies may require industries and wastewater treatment facilities to obtain permits for discharging effluent into water bodies. These permits often include conditions related to effluent quality, monitoring requirements and reporting obligations. Compliance with permit condition is enforced through inspections, penalties for violation and other regulatory mechanisms. Monitor and enforcement. Effluent testing and monitoring play a crucial role in enforcing regulatory requirements and ensuring compliance with water quality standards. Regulatory agency may conduct routine inspection of industrial facilities, sample effluent discharges and analyze sample in accredited laboratories to assess compliance and regulatory requirement. So, this is equally monitoring and reinforcement is very, very important. Capacity building. Developing countries may face challenges related to limited technical expertise, laboratory infrastructure and financial resources for effluent testing and monitoring. International organizations, donor agencies and development partners often support capacity building initiatives to strengthen regulatory enforcement, enhance laboratory capabilities and improve compliance with environmental regulations. Public participation and awareness. Effluent testing regulations may involve public participation and engagement to raise awareness about environmental issue, solicit input from the affected communities and promote transparency in decision making processes. Public access to information on effluent quality, regulatory compliance and environmental impact can empower communities to advocate for stronger environmental protection measures. And I will give you an example of Center for Science and Environment. It is an NGO in New Delhi which does this because they are spreading the awareness of any polluting site that is noticed and that needs to be rectified. International cooperation. Developing countries may collaborate with international organizations, neighboring countries and donor agencies to address transboundary pollution issues, share best practices in effluent testing and regulation and access technical assistance and financial support for improving environmental management practices. Effluent testing regulations in developing countries are essential for protecting water sources, safeguarding public health and promoting sustainable development. Efforts to strengthen regulatory framework, enhance monitoring and enforcement capacity and promote international cooperation can help address environmental challenges and achieve long-term sustainability goals. So, now even the international companies are insisting that these practices should be followed by developing countries also, because eventually we have one globe, we have one earth, and that earth has to be kept safely for the times to come. Hence, the so much of importance is given to sustainability. Therefore, one should switch over to eco-friendly textile processing. Eco-friendly textile processing aims at minimizing the negative effect on the environment. The textile wet processing units discharge a large quantity of effluent comprising of a wide range of chemicals, that is, dyes, auxiliary chemicals which contain metals, ions sometimes. In the application of reactive dye stuff, where it is due to fixation yields on order of 50 to 90% and high concentration of unfixed hydroxylates may be present in the waste liquor. Depending on the type of chromophore used, metals such as copper, nickel or chromium also could be present. According to Hostman, a systematic approach to shift average production towards clean technology should be followed as per the sequence: avoid, reduce, reuse, recycle or biodegradable material should be used. Environmentally speaking, wet cleaning has many advantages over dry cleaning, including minimal emission, less toxic raw materials and no hazardous waste. With dry cleaning, the concerns are primarily with air emission, worker safety and hazardous waste management. With wet cleaning, those problems including worker safety are greatly decreased, but wastewater concerns are somewhat increased. So, we have many eco-friendly textile processing options. Now, it is time to shift to that. So, what are the benefits of actually looking into eco-friendly textile processing? Eco-friendly textile processing refers to the use of environmentally sustainable practices and technologies throughout the various stages of textile manufacturing. This approach aims to minimize the environmental impact of textile production while promoting resource efficiency, reducing pollution and ensuring worker safety and health. Here are several key strategies and technologies used in eco-friendly textile processing. Sustainable fiber selection. Choosing environmentally sustainable fibers such as organic cotton, hemp, bamboo and recycled polyester can significantly reduce the ecological footprints of the textile production. These fibers are often produced using organic farming methods, require fewer pesticides and synthetic fertilizers and have low water and energy requirement compared to conventional fibers. So, one thing is that we can switch over to sustainable fiber by selecting them. Water conservation. Implementing water saving technologies and practices is crucial for eco-friendly textile processing. This includes the adoption of closed loop water recycling system, water efficient dyeing and finishing processes, and the use of low water or waterless dyeing technologies such as air drying or dyeing or foam dyeing, and even sometimes supercritical fluid dyeing. Energy efficiency. Improving energy efficiency in textile processing can help reduce greenhouse gas emissions and lower production costs. Energy saving measures include upgrading machinery to more energy efficient models, optimizing production processes, using renewable energy sources such as solar or wind power, and implementing heat recovery system. Chemical management. Minimizing the use of hazardous chemicals and substituting them with safer alternative is essential for eco-friendly textile processing. This involves adopting eco-friendly dyeing and finishing chemicals, implementing chemical management system to track and reduce chemical usage, and ensure compliance with strict environmental regulations and standards. So, wherever it is possible, if the chemicals can be managed and used optimally, that is what is also a kind of eco-friendly textile processing. Waste reduction and recycling. Implementing waste reduction and recycling initiatives can help minimize the generation of textile waste and reduce landfill pollution. This includes recycling textile scraps and post-consumer waste, repurposing production waste for other application, and exploring innovative recycling technologies such as chemical recycling and mechanical recycling. Sustainable textile finishing. Adopting sustainable textile finishing techniques can help reduce water and chemical usage while achieving desired performance and aesthetic properties. This includes techniques such as mechanical finishing, enzyme finishing and plasma treatment, which require fewer chemicals and produce less wastewater compared to traditional finishing methods. Certification and standards. Seeking certification from recognized eco-labels and standards such as Global Organic Textile Standard GOTS or OEKO Text Standard 100 and Blue Sign can help verify the environmental and social sustainability of textile products and production processes. These certifications provide assurance to consumers and retailers that eco-friendly practices have been implemented throughout the supply chain. So, GOTS and Ecotex are some of the, and Standard 100 are very important certification and standard methods which give a label that all the processes have been taken care in the textile processing to be eco-friendly. Overall, eco-friendly textile processing involves a holistic approach that consider environmental, social and economical sustainability principles. By adopting sustainable practices and technologies, textile manufacturers can minimize their environmental footprint, meet consumer demand for eco-friendly products and contribute to a more sustainable future for the textile industry. Reducing the environmental impact of textile effluent. Reducing environmental impact of textile effluent is essential for sustainable textile production, and this is how we understand that why we should move from normal textile processing to eco-friendly textile processing. So, here are some of the recommendation for managing textile effluent more effectively. Implement water conservation measures, adopt water saving technologies and practices such as closed loop water recycling system, water efficient dyeing and finishing processes, or sometimes even doing waterless dyeing. Utilize eco-friendly chemicals wherever it is possible. Substitute hazardous chemicals with safer eco-friendly alternatives in textile processing. Choose low impact dyes, chemicals and finishing agents that minimize environmental pollution and toxicity in effluent discharge. Optimize dyeing and finishing processes. Improve process efficiency and resource utilization to minimize waste generation and effluent pollution. Implement process optimization techniques such as batch optimization, recipe management and equipment upgrades to reduce chemical and water usage and improve product quality. So, reducing the environmental impact of textile effluent is the only way out. Treat effluent before discharge, install and maintain effluent system to remove pollutants and contaminants from textile effluent before discharge, monitor effluent quality, regular monitoring and analysis of effluent quality to assess compliance with regulatory requirement and to identify opportunities for improvement. Implement comprehensive effluent testing program to measure parameters like color, COD, BOD, pH, TSS, heavy metals and dye concentration. Invest in research and innovation. Support research and development initiatives to develop innovative technologies and sustainable practices for managing textile effluent. Collaborate with industry partners, academic institution and research organization to identify and implement cutting edge solution for effluent treatment and pollution prevention. Educate and train personnel, because unless and until we train our own personnel, this feeling or this thought that we have to reduce the environmental impact of the textile effluent, we will not be able to proceed for a better world, for a sustainable world, for a world which is environmentally clean. To engage with stakeholders, collaborate with government agencies, non-government agencies like NGOs, community group and other stakeholders to address environmental concern and promote sustainable practices in the textile industry. Participate in multi-stakeholder partnership industry association. By implementing these recommendations, textile manufacturers can minimize their environmental footprints, reduce pollution and contribute to developing of a more sustainable and responsible textile industry. So, in conclusion, textile effluent testing plays a very crucial role in ensuring environmental sustainability of textile manufacturing processes. Effluent from textile operations can contain various pollutants that pose risk to ecosystem, water resources and public health if not properly managed. Effluent testing allows textile manufacturers to monitor the quality of wastewater discharge, assess compliance with regulatory standards and identify opportunities. And as I had already mentioned, that effluent testing must involve color, COD, BOD, pH, total suspended solid, heavy metals and dye concentration in analysis. Then only we will be able to minimize their environmental footprints by strategizing a good remediation plan. So, the key recommendation for effective textile effluent management including implementing water conservation measures, utilizing eco-friendly chemicals, optimizing dyeing properties and finishing processes, treating effluent before discharge, monitoring effluent quality, investing in research and innovation, educating and training personnel, and engaging with stakeholders can only improve the situation. With this, we have come to an end of this lecture. Thank you.